Well, everybody's doing okay.
Good, good.
Great, great. Um, well, I should just let you know that I have been running some models myself, this time looking at the advice networks. And so far, interestingly enough, advice seems to feature both reciprocity and transitivity, which surprised me a little bit. You know, I thought advice would be a little bit more hierarchical than that. But it appears that there's a tendency in these networks for people to be more like to sort of mentor each other, shall we say? At least that seems to be part of the dynamic, and that's a little bit surprising and interesting. Because another model might have imagined that you uh, would have a central person typically in a house to whom a lot of people went to for advice, because this person was, I don't know, older, more experienced, whatever, higher status in some kind of a way. But once again, we kind of see evidence here of how relatively unhierarchical these houses tend to be. Lenny, I guess, given your experience with Oxford House governance and organization and everything like that, that may not be a big surprise, but it's certainly not to be taken for granted. I guess that's the way I would put that. Okay, tell you what, let's continue our discussion from where we were last time. Let me just switch to the correct project here. By the way, Lenny and Ted particularly, but anyone else too, I just finished updating my JML utils package, generalizing the send email function. It still has a limitation, which is that you have to send it from a Gmail account, because the way that you can use code to access an email server to send an email varies from one platform to another. And so far, I just haven't had the time to figure out how to do it with, I don't know, Microsoft Exchange or something like that. But I have figured out how to do it with Gmail. And since anybody can have a Gmail account if they don't already, this isn't really too much of a limitation. Plus so now you can go in and there's two functions. You set up the email, which requires you to give it your Gmail account, not the @gmail.com part, just the first part. And then you can do a send email, say after an R-Siena run finishes, because it can take a couple hours. And you can send it to, you'll have to send it from your Gmail account, whatever that is, but you may send it to any other email account that you want. So maybe you want to send it to your DePaul account or something like that. You can do that. And I'm going to push that up to GitHub in a minute. And if you don't have access to it on GitHub, I'm also going to make available a binary that you can install. So it's just not a terribly important thing, but it's kind of handy to, to have the computer send you an email after your run finishes. Okay, well, that having been said, I'm going to share the screen. Ready, 1, 2, 3, share. Okay, and everybody should be able to see my RStudio screen now, right? No, Phil doesn't see it. Oh, you know what? I just unshared it. Try it again. All right, that's better. Yes? Okay, great. Yeah, sorry about that. I always forget to hit the share button. Okay, so last time we were kind of putting the finishing touches on how you go about setting up an R-Siena model. Just a very brief recap. In the I've set the R-Siena setup branch of RHNets up in a way that any analysis run uses two different scripts. One of them is the setup R-Siena models script, And that is supposed to be pretty general, but we may add to it from time to time. The idea is you're creating objects there that you can use to put into an R-Siena model, but it stops short of actually creating the bundle of stuff you need to set up the model, a specific model, I should say. Okay, and then we have run R-Siena model scripts. This one has a .fr on it, which tells me that it's, you know, about modeling friendship. And just to recap, we created a bunch of R-Siena specific data objects out of our objects that were formatted in the proper way in the setup script. And then we combine them all together in what's called the data object in this line here. By the way, can everybody see the screen okay, or should I make it bigger? I can make the, just if nobody says anything, I'm going to leave it the way it is because it's easier
little
for me
bigger
to
would
see
be
it.
great, John.
Okay. All right. We have a little bigger. And is that okay, Lenny?
Yeah, it's better.
Okay. I mean, I don't want to make it painful for you. All right. I'll assume that's all right unless somebody says otherwise. All right. So here we use the Siena data create function to combine these R-Siena data objects that we created in the previous script. And this is the sum total, again, of the variables which can provide effects or predictors, if you will, in an R-Siena model. They are either directly one of these objects or something that can be a function of one of these objects. So we have the network, FNet0SD, the friendship network, recovery factor, we have fixed covariates of sex and age, and also the amount of time that the person was in residence when they first surveyed. I added a new one, rs.black, which is a dichotomous variable indicating if the individual is African American or not. This based in part on some recent results that we had, Mike, based on ones that you did and that you and Lenny are now writing up in the paper. And then finally, we have the composition change object, CCSD here, which will tell R-Siena when individuals were, what waves an individual participated in, basically. Okay.
Hey, John, can I
yeah.
add the RS black variable to my script because I have it open now, or will that change anything?
You can add it, but remember that you will have to then include the updated DT_obj thing over here in creating subsequent objects. So for example, notice the effects object here is a function of that DT_obj. And so you'll have to make a new one of those too. And then, you know, the effects object is part of the Siena 07 call. So you'll have to include the newly updated effects object there too. So yes, I mean, the answer is sure, but you just have to make sure that you cascade the changes forward. Make
Thank
sense?
you.
Sure.
Yes, sir.
And I believe that in the latest version of R-Siena setup, this branch here that I pushed up to GitHub, that rs.blk is included. So that might be the easiest way for you to deal with this, is just to, you know, to pull that branch again. I'll pull the whole repo, obviously, and then you can switch to that branch, and you know, you have a choice of things you can do from that point. Okay. All right, and we noticed here that we get a descriptives report by executing this function. The name will be whatever this is, .text. We create an effects object, which, as I mentioned before, is a function of the data object that we created earlier, and which will give you a table of all of the possible effects in the model. And you can get an HTML version of this by executing the effects documentation, which will then give you a this fobj HTML object. And I'm going to open that and just have a look at it. and this is what that looks like. I've gone through this before, but I'll just go through it again briefly. This is essentially a table of literally all of the possible effects that you can include in the model. In some cases, they're somewhat flexible and they allow you to make some choices of your own. But for the most part, including predictors in a model is a matter of selecting different rows out of this big long table. And you can see it's really a big long table, right? There are some, here you have an effect that's a so-called unspecified interaction, which you can specify. There's a way that you can do that with an include interaction function. And we'll talk about that in a while. But for the most part, these are just effects that you may select if you want them to be predictors. Let me finish the nuts and bolts of setting up the model, and then I'll talk a little bit more about effects. We did talk about that last time, and I showed you examples of the reciprocity effect and the transitivity effect and a similarity effect and some others like that. I don't think I need to go back through that, but I want to talk about effects kind of in general and what they mean and things like that. But let's leave that for a little while. All right, so finally, having created all of these models, oh, wait a second, there's one important one that I forgot. Oh, no, here we are. No, never mind, here we are, we're right here. This function here is called Siena model create, obviously. And what this really does is it sets up a set of specifications for how the analysis is to be run. A lot of these parameters here are kind of technical in nature, like Dolby is a estimation feature that supposedly is more efficient. Do we want to use maximum likelihood or not? Generally speaking, the answer to that is false. Again, that's a subject I'll put off to later. There's a couple of different estimation methods. Maximum likelihood can be good in smallish networks. It's more accurate, but it takes a long time to run, partly because it's not implemented to run on multiple nodes at once. Okay. The key things to note here are, you give it a project name. This will create a script called thisname.txt, which gets added to every time you run a model based upon this RF mod fr.1 object, which is going to be included in the call to the estimation function. And usually you repeatedly use this, which means that you repeatedly get your analyses tacked onto the end of this script here, not script, this text file. The model type is a place where you can, basically what you do here is you just specify the name of any and all networks in a vector. If we had more than one network in here, which you can have, there would be another one of these, like, should be a comma. Okay, and so forth if you have other networks. Basically, this is just telling you my model type includes these networks, and it's what's called a one-mode network, which means there's only one type of network involved. There's something called a bipartite network, which can also be modeled in R-Siena. Bipartite networks have two different types of nodes. So for example, you could have a node consisting of organizations, or a node type consisting of organizations, and also a node type of individuals, each of whom is a member of that organization. And it's possible to dynamically model networks like that too. Okay, but generally speaking, we don't need to worry about that. It's actually possible that we could use a bipartite scheme with recovery houses at some point in the future, which is Interesting. That's an idea I just never thought of until just this moment, but it's something we could think about. Anyway, hold that thought. And then also, if you have a behavioral variable, you have to give it a specification like this also, which just means that it's a regular dependent ordinal variable behavior. Okay, so we create this. Oh, one important thing is the use standard inits. I mentioned this last time, but I'll mention it again. The first time you run a model, you pretty generally want to set this to T, to true, because that way R-Siena will calculate some standard, using a standardized method, it will calculate the initial values for the estimation run. And usually they're not too far off and it allows the estimation to go ahead well, but subsequently we will set it to false, because what we'll do is we'll use whatever parameter values were estimated in the previous run as we go on to the next one. In general, it's recommended in R-Siena to use what's called a forward selection process, where you start out with a simple model that's pretty easy to estimate, contains effects that you're pretty sure will probably be relevant. Some cases that can be a challenge, but usually with social networks consisting of human beings, not so much. And then from there, you go on to add other more complicated effects, in each case using the parameter values that the last run ended up with. Of course, it won't know about the new parameters, but that's not so important as long as it's got a pretty good idea for how most of them should be set. Now, down here, I think this is kind of where I left off last time. This is where we can update the effects objects to include a number of effects that are not included by default. By default, a model always includes so-called rate effects. Rate effects are basically just a model-based measure of how much change there is between waves. And so if I come down here and look at my model, right here. Oh, geez, you know what? I got so carried away there. I forgot to load my packages and load my environment. That's always the first thing you want to do when you come into RStudio and you open up this repo. You've got to load your packages and do that first. And here they go, they're loading. And these packages are packages that are necessary either to run R-Siena or to run the code that's included in my script. And then we are going to load the environment, and we see these variables and things appearing here as I do that. Okay, this will be better. By the way, I just want to highlight that one really nice thing about RStudio that I encourage you to use is this window here, which will show you our markdown that you put in as kind of navigation guides in your script. So for example, you'll notice that I have, this is not inside a chunk, right? This is just in the script itself, or the notebook itself. 2 crosshatches. Well, a crosshatch is basically an indentation marker for a piece of text over here. And you'll notice that this lookup effects here corresponds to the lookup effect over here. So if I want to quickly go different places in the script, I can set these kinds of markers, which not only help me see where I am, but they help me move between different spots. So that's really something worth looking at. Our markdown is kind of like LaTeX, but it's a lot simpler, and it's very easy to learn how to use the basic stuff, and it's a great way to kind of mark up your script and make it easier to fumble through it, especially if it's a really long script. Like I have some scripts that are like, I don't know, 2,000 lines long, and it's really easy to forget where you are there.
John, can you show where you basically get that little script? What icon you have to press on so that it'll pop up?
Yeah, it's right here. Can you see the little thing that looks like different lines at different levels of indentation? It's kind of small there, but everybody will have that in their script window at the top. And so all you have to do is click on that, and it toggles the your outline, if you will, of your document. Cool? Okay.
Yeah.
So anyhow, now I'm going to look at this. Oh, shoot. I still don't have an effects object. All right, fine. I'm going to make one. Yeah, this being a template, I don't necessarily have all the objects referenced in the script included in this environment. I include the ones that are necessary to begin the creation process, but I kind of leave it up to you to modify the script in regards to R-Siena objects in a way that suits what you want to do. So if something isn't there, all you have to do is go back further into the process and create it, you know, from whatever code is already there or some modification that you do. All right, so let's go ahead and create the data object. Well, first of all, let's see if it's here. No, it's not. So I'm going to go ahead and make it. It's just take a few seconds here. By the way, if you ever want to see what a data object looks like, you can always go over to this window here and you know, take a look at it. And it's going to be a list. Fundamentally, that's what it is. This list includes the nodes, the observations, in this case, you know, the number of longitudinal observations, dependent variables, constant covariates, time varying covariates, dyadic covariates, and dyadic time varying covariates, all of which are not present in the current analysis. But we do have 4 constant covariates and 2 dependent variables, namely the network and the recovery factor, right? And we have a composition change thing. So that's what a data object looks like. That's what R-Siena makes it into. And don't worry about this message here. I don't even know why that happens. Okay. So I was looking at the, let's go here and look at effects. Oh, geez, I'm sorry. I still haven't made the effects object. Here we go. Now I can look and see what's in the effects object. So basically, when you set up a model, R-Siena will give you a starter model, which is very simple. As I noted before, it consists of 5 rate parameters for each dependent variable. Dependent variable can change endogenously in the model, remember. And why 5 when we have six waves? Well, it's for the interwave period, because remember, we're talking about change in these models. So we have a period 1 to 2, that's period 1, period 2 to 3, that's period 2, period 3 to 4, that's etc., on down to 5 to 6, which is period 5. Cool? And it includes a reciprocity and an out degree parameter. And then for the behavior variable, it only includes so-called shape parameters, which basically just have to do with the how the recovery factor changes as a function of its own value. Generally speaking, what we find is that, you know, there's a linear shape. It's going generally up or generally down, and a second order effect, a quadratic shape parameter, which quite often is negative, meaning that it has a sort of a convex shape, meaning that there is some centrally preferred value of RF, preferred in the sense of it's the most typical in your study. Okay, now this is great, but it's not really much of a model substantively speaking, and we're going to have to add effects to this. So why don't we go ahead and do that? The way you do that is by using the include effects function. So unlike some models that you might be used to where you just specify, let's say, a formula or maybe a list of predictors or something like that, here you actually have to run a function, because what's going to happen is it updates the effects object. The effect object is a central place where all of the effects to be modeled are centrally located for the benefit of the estimation program. And it's not quite as simple as just providing an unvarnished list of variable names or something like that. Let's look at one of these specifications a little bit. And I'm also going to pull up the effects object doc again. Okay. Yeah, there we go. Great. Okay. So let's suppose that I'm interested in, I'm going to add something to this. Let's suppose that I'm interested in whether individuals who have been in residence for a long time are more or less attractive as friendship partners, are more or less likely to befriend others, and are more or less likely to choose each other as friends. Because those are really reasonable hypotheses, aren't they, about how the network dynamics might work? I mean, it would figure that if people have been around the house for a while, they'd know each other better, they'd be more likely to be friends. You could argue the question of who they choose as friends either way, because although, you know, yeah, they may be closer friends with people that have been in the house for a while, maybe they also feel a sense of obligation to help out newcomers. And so the people who have been there the longest might disproportionately tend to try to befriend others who have just arrived, relatively more so than a relative newcomer would. So you could argue that question either way. You know, are they cliquish or are they not cliquish? That would be one way to put that question.
So John, is it possible that they might early on just be friends, but that over time they could become close friends?
That they could. And in order to test something like that, the best way to handle it is with a more advanced technique where you actually include two friendship networks, one of which is basically a subset of the other. And you have like a loose criterion friendship network. To use our specific definitions, maybe you say a person is a friend if he or she endorses person J is a good friend or a friend. I think that was the language that we used. Or maybe it was close friend or friend. I'm not sure exactly, but it's not that important, but you get the idea. And then another network, which is only good friend or only close friend. Obviously, you have to be, if you're a close friend, then you're a friend, but not conversely. So it is possible to transition in this kind of idea from not being a friend, at least according to either of these two definitions, to being a friend to being a good friend. And each one of those transitions can have different predictors, right? So that would be the way you would want to go about testing that. Specifying such a model is kind of advanced, and it's really more than we can talk about right now. but it is possible to do that. I mean, it would be cooler if there was a way that you could just have people rate each other on goodness of friendship and have that treated as a continuous variable where the model is kind of able to try to fit an estimate of that closeness against the data. As far as I know, that is not possible at this time, although it is possible in a test version anyway to have continuous behavior variables. Up to this point, up until very recently, you could only have basically ordinal variables so that you would have a discrete transition between each ordinal level. That's kind of the way it worked. But now it's there's a recently developed change to the algorithm so that you can use continuous variables. Well, that's a digression for right now. All right, so here's the basic syntax for how you would go about adding show you that again. An effect, which is going to be, well, we're actually going to go ahead and do this. What I want to do is I want to add an ego effect, which is to say a characteristic of the person doing the choosing, and an alt effect, which is a characteristic of the person being chosen, and then a sim effect, which is similarity on some variable between the person who's doing the choosing and the person who's been chosen. I'm allowed to specify all three of these names, and these names are short names, of which there are many different types. But what I want here is I want to find out which of the rows in this table over here correspond to an ego effect of my rs.inresL variable, which is the amount of time you've been in residence when you first arrived. Log transform, that's what the L is, okay? And so how can I do that? Well, what the syntax does, broadly speaking, is it says, okay, this row is going to apply to the network as opposed to the behavior dependent variable. It's going to be of type eval, which I'll explain about in a minute. And this really badly named parameter here called interaction1 is going to be the actual covariate that I'm looking for. So what I'm looking for here, here's interaction1, okay? So I want to find out, first of all, the name is going to be fnet0sd. So that's where name comes in. I'm telling you, it's one of these rows that has fnet0sd as its name characteristic. But there's a lot of those. So I haven't narrowed this down to any particular set of interesting subset of variables yet. Well, okay, some of these are evaluation types and some are not. Again, you don't know what that means yet, but just let's let that slide for a second, okay? So it's going to have that in this column, but there's still a lot of those too, all right? But hopefully only one of them will have, well, only three of them will have a short name of egox or altx or simx, and also this is its inter1 characteristic, okay? So let's just go down there and see what we find. Well, here we see inter1 of rs.sex. Well, we're getting warm. Somewhere, this is all the effects that have to do with using sex as a fixed covariate. See, if you wanted to use sex as a fixed ego characteristic, this row here might be relevant. And what this row here would talk about would be whether there's a tendency for people who are male, whether there's a differential tendency for males and females to extend ties to others. If I included this effect here in the model, number 198, and I found there was a positive parameter, well, I happen to know that 0 equals male and 1 equals female. That would mean that the individual with a higher value on sex, which in this case would be females, would have more of a tendency to make friends. Just in general, they would have more of a tendency to make out choices, okay? If it was negative, it would mean the opposite. It would mean that men would be the ones who had more of a relatively more tendency to extend ties to others, okay? Please ask questions if any of this is, if you want me to say it again, or if it sounds unclear or whatever it might be, okay? All right, so anyway, we're trying to find rs.inres_L because that's the predictor of interest here. So let's just keep going here. Well, there's age. So remember, these are all things that we included in the data object, right? Ah, here we are. All right, so all of these rows here pertain to rs.inres_L. And we can see we have a lot of different classes of effects here as suggested by the long name, which is kind of like a descriptor, and the short names. These things over here are the short names. And as a shorthand, I believe that, yeah, you can specify multiple short names if you wanted to include a bunch of different effects associated with this particular variable here. So what are the ones that we've specified? Well, lo and behold, there's ego X, right? So we have an ego X effect, and the type is eval. I've already specified that type would be eval. And I've specified the inter one is rs.inres_L. So that's going to match this row for sure, right? It could match others if there were others that had the same values of name, short name, type, and inter one, but there aren't, okay? So that spec here, ego X and these other things here, will pick out this row. However,
So
I include a, what?
how come you have 4 different versions of ego X?
Aha, because there are 4 different types. And now I will explain that since you so perfectly timed that question, Lenny. An evaluation effect basically is symmetrical in terms of whether it predicts upward or downward movement, okay? So it assumes that the parameter is the same for creating a tie based upon the value of the amount of time you've been in residence as it is for dissolving one. But if you think about that for a second, that's not necessarily true, right? I mean, it might be that length of time in residence is really important for predicting formation of new relationships. But then once that relationship is formed, it doesn't really predict whether the relationship will continue or not, right? That's perfectly reasonable, right? So if you thought that, then what you could do is you could separate your ego effect into 2 effects, okay? And so instead of using an eval, which assumes that creation and dropping of effects is a symmetrical process and the parameter is the same for both, you could have a so-called endowment function, which is basically about what predicts time maintenance or not, time maintenance or dissolution, or a creation effect, which is, as you might imagine, what's the parameter for what, relating amount of time in residence to whether the tie is created. So basically, it just is a way to allow an asymmetrical process to allow the time in residence to asymmetrically affect the creation of ties versus the dissolution of ties. Okay? Make sense?
Yeah.
Then finally, GMM is utilizes a different methodology for the estimation. And it's something we don't have to go into right now. And so it's not really relevant to us at the moment. So generally speaking, when you start out adding an effect, you will just use an evaluation effect because it's one effect and you don't need one versus two. But it's often quite reasonable as your model gets more sophisticated to split that off. You get rid of the evaluation effect, right? Because these two here completely take the place of it. And you substitute two other effects, an endowment ego X effect and a creation ego X effect, which can have two different parameters for tie formation and tie creation as a function of the amount of time the person has been in residence. Okay? All right, hope that's clear. Good question. But anyway, all right, so this row here is going to get picked out by my call to include effects. And so will this one. Right, there's an Alt X. There's my interaction one. There's my type. There's my short name, unique row. And then finally, the SimX effect. Now I'm looking for SimX here in this same business. There it is. And this row will be picked out too. Okay. So basically this call to include effects will add 3 new effects to the model. And let's just try that. And it confirms down here that the include is true. True, true, true. And let's go down and look at the effects now and see how that changed. And voila. Now I have the alter, ego, and similarity effects for InResL included in my model. Okay. Now let's suppose that I want to get rid of those. Maybe they didn't work, or maybe I changed my mind, who knows. In that case, all I have to do is take this and add, oops, sorry, fat fingered that one, and just say include equals F. Include equals T for true is the default. So I didn't have to include it. I could have, you know, when I ran it before, I could have just had that as a spec, all right? But now I can get rid of that, these 3 parameters by just running exactly the same code. And it says, yeah, sure enough, it got rid of it. And let's just go check to make sure. And lo and behold, we're back to the original model. Okay, so that's how you go about adding effects to your model. And of course, you can read about the syntax. The syntax is a little broader than that and explained a little more clearly by going to the help text for R-Siena or R-Siena test. And so basically any effects that you can include, well, no, not quite. Most of the effects that you can include, which is to say the effects that are listed in this table, can be included by virtue of running the include effects parameter. And it's really our function, I mean, and it's really handy to have this window open just to make sure that you specify all of the stuff that needs to be specified to pick out the right row. And you can always check and should always check that you have indeed specified the model the way you want by running that just, you know, specify the name of the effects object and run it, and it'll give you all the parameters in the model right now. And that allows you to double check that the model is specified the way you want. Okay. All right. Questions so far? We've been kind of going hot and heavy here.
So John, one thing that'd be really helpful, I'm not sure we're going to get to it today, but being able to understand, you know, the significance of the outcomes.
Well, one thing that I can do, we're just about ready to look at the specification of the actual model estimation. And so we'll take a quick look at that. And then because of the fact that these models take, you know, an hour or two to run, I'm not going to actually run a model, but I'll show you output and we'll walk through that, okay? That sound good?
Sure. Yeah.
All right. All right, let's do that. So we'll come down here.
The only thing is, Ted can tell us whether his model ran. If it did, maybe we could take a look at that.
Sure, that'd be great. You know, any output is interesting to look at, and I'd be delighted to take a look at that.
Mine's
Okay.
on phase 2, subphase 4, iteration 24. So I'm still going. It says like about 75% there.
You're going to be a while yet. Yeah, we probably aren't going to have time to look at that. It might finish within a half an hour or so, though. So if we're still online, then we can take a look. And just keep an eye on it for us, Ted, and let us know. Okay, so this is Siena 07 is like the ultimate estimation program. It's the one that actually runs the model. You will notice here that we have a this rf mod.fr.1 was created by Siena Model Create, or equivalently Siena Algorithm Create. So this is the one that kind of instructs Siena 07 as to how the model should run. You know, should I use maximum likelihood or a different method? Should I, you know, what should I call the output? All that other stuff that we remember from before. And here's our data object. You're giving it the data. Here's our effects object, you know, which has the specific effects that are in this model, because we just saw what was in this effects object, right? And it wasn't all the effects, it was only the ones that we wanted. Now, the next two are technical but important. Use cluster and number nodes. If you have multiple cores on your computer, then you can use, then some of this analysis can run in parallel. Not all of it, but some of it. In particular, the estimation part, phase 2, will run, estimation runs, in this case, 7 of them at once, and then it will average the results, update the parameter vector, and then go on and do another 7. Average those results, update the parameter vector, etc., which in general is quite a lot faster than if you just use one core. So if you have a multi-core machine, I recommend that you say use cluster equals true, which means, you know, use the multiple cores you have available, and set the number of nodes to 1 less than the number of cores you have. So I have an 8-core machine. I set it to 7. Because you want to leave something available for the system to do what it needs to do. Otherwise, things can get kind of annoying. Having said that, by the way, it's still probably a better idea if you can figure out a way to have an analysis computer and not use your own personal computer, because it's going to really slow down whatever else you try to do on that while the analysis is running, in case that's not crashingly obvious. I have an analysis server that I use at ORI, which is very handy. In fact, there it is, and it's running a model right now. Oh, looks like it just ran a model. Oh, nice. Okay. But anyway, it's called RStat, you know, and it's an 8-core, quite fast server. And I'm looking at it using remote desktop. Okay, now we're back to our my computer here in my home office. Okay, so there's that. Then there's the Prevance computer here. Remember our computer, specification. When you, after you've run a model, you can give it the results object from a previous model. I mean, in this case, they're the same, which wouldn't make any sense. But let's suppose that I was on model number 2, having already run model number 1. I would give it model number 1 as the Prevance. And then R-Siena, when it runs, starts out this estimation, will go back, find all the parameters in mod.fr.1, which match the ones in the current effects object, and use those parameters as start values. So it really improves the efficiency of the estimation, and it maybe clarifies why we recommend a forward selection process, because the although it's always possible for parameters to change as you add new effects to the model, unless those effects are quite strongly correlated with new effects. In general, they'll tend to be around the same value. So this is considered to be a better way than other ways. So for example, you don't want to start with a really complicated model and then start kicking out irrelevant effects, because your estimation routine might not have done a great job of estimating that complicated model if it doesn't have anything to go on. Okay, so that kind of takes care of the nuts and bolts of setting up and running an R-Siena model. Good time to pause for questions, if any. Of course, you will have more questions when you actually start to do it. As Ted and Lenny have already found out, they began running some recently. I'm not sure exactly when they began, but they both have models running on their computers now. So we'll see what happens with those.
John, could you just real quickly summarize? We looked at friendship, we looked at willingness to loan and advice seeking in these 42 houses over kind of a couple of years, every 4 months. You're finding, is it comparable results across those three types of relationships, or are they different from what you're sensing from looking at them?
Well, of course, they're different relationships. And so there's no reason to think that the dynamics that predict the way they change over time, nor how they interact with the recovery factors, should be the same. No reason to expect that at all. And so what I would say is that almost everything that I'm finding in these analyses is interesting and not to be taken for granted, if I may put it that way. I can show you a couple of the results that I've gotten already as a way of, by way of putting a little meat on those bones. Why don't I do that? So here I went back over to my RStat server, and I'm going to take a look at the all right, I'm pretty sure this is a friendship model here. Now I'm opening a text file containing those results. Why don't we just go right up to the top of the file, because this is sort of like the Hubble Space Telescope. As you go further back in time, you go further back in in distance too. And we start with a simple model and we see how it got built up. So lo and behold, here we have a friendship model, and look at the specification here. We got our rate parameters. We've got an out degree effect, which is basically what is the general tendency on average to people tend to, on average, how many friends do they tend to select would be a good way to put it. And it's kind of graded on a positive negative scale, where negative would mean fewer than half and positive would be more than half, basically. Although it's not a 0-1 standardized scale. We have reciprocity, which would be the tendency where, given that somebody at the start of a particular wave has extended a friendship tie to me, am I any more likely to then extend one to them? And the answer to that will be indicated by a positive parameter here. You can see it starts out to be 0. Transitive triplets, we talked about that before, but that's just basically the tendency of if I'm friends with Joe and Joe is friends with Fred, does that make it more likely that I will become friends with Fred? And then 3 cycles are basically a measure of hierarchy. A 3-cycle is a situation where, you know, I choose Joe, Joe chooses Fred, Fred chooses me. In cases where, I'll just explain this very briefly, in cases where that final tie is not likely to happen, we generally think that that's indicative of hierarchy because, you know, I choose Joe, Joe chooses Fred, but Fred is low on the status hierarchy, so he doesn't get to choose me back as a friend, right? It would be as though, you know, the big boss chooses the boss who chooses me, that type of thing. That doesn't give me license to now befriend the big boss. You see what I mean? So we usually think of this as indicative of friendship hierarchies in friendship networks anyway. And so it's a good thing to include because it's a very common dynamic in many social networks. Interesting question as to whether that obtains in a place like a recovery home, though, where things are supposed to be very egalitarian. All right, so those, up to this point, up to here, those are the only effects that I have predicting the network tie formation. Now these effects down here are the recovery factor equation. So this is basically an equation where the dependent variable is the network ties. This is another equation where the dependent variable is the recovery factor. And in addition to having rate function parameters, which basically just tell you how much change there is between each set of waves, there's also these shape parameters. So we don't really have any substantive predictors here at all. We just have a indicator of how much change there is in the recovery factor and what tends to be the shape of the recovery factor preference function, you might say. Okay, so now things are going to get more interesting as I go along here, and this is the, okay. So at the end here, and this is the end of the estimation run, two things are of interest. This stuff up here tells you how the convergence went, and it does so parameter by parameter. And the important thing to see here is this T ratio. The T ratio should be close to 0 in absolute value. Basically, they're just the significance of the difference between consecutive estimates of that parameter and whether those differences are something like, well, and scaling them relative to the standard deviation of parameters. And so the closer to 0 they are, the better off you are. Notice that there is a note here that one or more of the T statistics are rather large. So let's see what it's finding here. Well, not really sure what it's seeing there, but I would say most of these are okay. And also the overall maximum convergence ratio needs to be, they like that to be under like 20. Well, look, it's 1. So I would say all things considered that despite what the automatic algorithm is telling us, the actual estimation wasn't half bad.
So John, I know when I was looking at this with Lenny and Ted, I think last week when we were first trying to go, get some of these packages installed into R. Correct me if I'm wrong. I thought I read somewhere that, we want those T ratios as close to 0 as possible, but it seemed like, was it something like 0.2 was sort of like a magical threshold in terms of the absolute value of those T ratios?
Yeah, that's probably true. And we can see that some of these are above that, okay? But another thing we have to consider here is the fact that it's a first run and that the initial values might not be too good and that the model might in general not be fit very well because we have so few parameters. So yeah, that's
Okay.
true. And that's probably why we're getting this error message, this warning message here. Because we can definitely see that some of these values are iffy.
So is there a danger with these models where you said like there might not be enough predictors in the model? Is there also a danger to or any issues with overfitting the model?
Yeah. Absolutely. Overfitting is always an issue in any model, right? Even if your results are statistically significant. But I would say that because of the fact that you've got an iterative algorithm and not a closed form solution, the tendency generally is if you've included too many parameters, you're not going to get very good convergence.
Right.
Because the parameters just don't have enough information to really be estimated, you know? And that will be reflected by the estimation algorithm kind of wandering around on the, the response surface and never really securely finding a good place, that you can really call optimal.
Right.
But you're absolutely right. Pretty much every consideration that you've ever heard about in a multivariate regression type model is a concern here. It may be expressed in a way that's a little unfamiliar, but it's still there.
Okay.
Good questions. Good questions. Yeah.
John, is there any way to monitor the program's process?
Yes, there is. And I will, I'll tell you what, I'll show you how that works in a minute by starting one. What I can do is I can just rerun this one. But let me just quickly show you that, what we found. So this information here should make us, well, if we add parameters to this model and find that this stuff isn't getting better, that might be an indication we're kind of on the wrong track, that we have one or more parameters in there in the model that isn't really relevant or somehow doesn't represent what's going on in a good way. And we need to sit down and think a little bit about, how we're specifying the model. If we add new effects and these parameters here improve and I lose this message and so forth and so on, then I'll be better off. Hey, by the way, you know what, Phil? I'm just now my brain's starting to work better. Yeah, the overall maximum convergence ratio should be more like 0.20, not 20. So indeed, this is not showing very good convergence.
Okay.
Even so, that can be okay on a first run. And I don't think you necessarily want to throw it out right now. It depends on your experience with these kinds of models. Okay. You might look at that and go, oh God, that's not, I'm not even in the ballpark. I really need to rethink this. Or you might go, well, I'll go a little further down this path and we'll see where we end up.
All right, that makes sense.
Okay, great. Thanks, and sorry for the misinformation. All right. Okay, so, but what we get here, look at this. The out degree effect is actually positive, which is unusual. And here's your standard error here. So the T ratio is going to be 0.559 over 0.249, which is going to be over 2. And that means that it's going to be statistically significant in the usual way that these things are considered to be statistically significant. And it's positive. That is an indication that friendship is not a particularly sparse quality in these networks. In fact, you could even go so far as to say that it's an indication that more friendships is better than less friendships. In most social networks, that is not the case. In most social networks, Sparseness is the rule. That is to say, you have relatively few friends out of all the ones you could have. Let's say in a social ecology of, I don't know, middle school students or something like that. You'll find this parameter is negative, indicating both sparseness and a tendency for people to not add the marginal additional tie because of the fact that that value is negative. It means that if you already have an endowment of a lot of friends, you're that much less likely to add one more. All right, that's what that negative parameter would mean here. But when we see a positive parameter here, the more friends you have, the more likely you are to add another one, if anything. So it's really an indication of tendency towards befriending others or getting along with others, or however you might want to interpret that substantively. And that's something we've consistently found in friendship networks in these homes, dating back more than a year, even before we had complete data. What about reciprocity? Is there a tendency for, if I choose you as a friend, for you to choose me back? The answer is yes, because the parameter is positive, and the standard error is, well, we would, if you divide this into this, you're going to get a T ratio of somewhere around 3.5, which is highly significant. Very low p-value there. So that there's good evidence that reciprocity is typical in these networks. And the same thing for transitive triplets. If I'm friends with Joe and Joe is friends with Fred, there's a good chance that I will become friends with Fred too. And as we mentioned before, we tend to think of that as a indication not only of similarity in, I don't know, preferences for friends, but also to some extent the fact that Joe's and Fred's friendship, along with my friendship with Joe, will tend to bring me in more contact with Fred and allow me the opportunity to become friends with him, which otherwise I wouldn't have, okay? So transitive triplets is a really good parameter to have in there when you don't have an opportunity variable and you want to standardize for the opportunity to become friends or to form whatever relationship you may be having here. It helps to control for that, and that's important because it gives more credibility to, for example, similarity on other specific factors. Maybe you both like baseball, or maybe you both, I don't know, come from the Northeast, or whatever the variable may be that could otherwise provide some basis for friendship. You know, like any multivariate model, you have to control for the most obvious potential confounders. And clearly an opportunity to be friends is something that is very important to control for. So that's why we include those. And oh, look at this, 3 cycles is indeed negative, meaning that 3 cycles are not likely to form, meaning that those, instead of that, these status hierarchy paths are likely to form, suggesting that there actually is some evidence of hierarchy in friendships. And it's significant, right? Because 17 into 36 is going to give you a value of something over 2. And we know 1.96 is the critical value for a T ratio. So there's evidence here of some hierarchy in these houses. Make of that what you will. But it's an interesting thing in and of itself. So that's kind of a really basic rundown of what we have from this very simple model. Questions about that so far?
So John, you have 0.05, 0.01, Bayesian. I mean, can you just tell us the differences as to, do we really believe 0.05 or 0.01 at this point in science?
Well, whenever you're doing modeling, there's always the question as to how good your evidence is. And I mean, I think we're all kind of implicit Bayesians at a certain level. I mean, if we look at a result and we go, yeah, I would have expected that from theory and from my past experience at looking at data like this and stuff. And I have a p-value that's less than 0.05. Well, that's nice, but there are occasions where I would find a p-value less than 0.10 to be interesting, perhaps, depending on, for example, how much power I thought I had for finding that effect, depending on my previous expectations and other, intuitive understandings of the situation. So that gets us into the whole question of whether this is a scientific area that's worth pursuing. Are these effects that I'm seeing here credible based upon what I was expecting and what I would expect under these circumstances? And the answer to that question is broadly, yes. The reason being mostly my experience in seeing these kinds of effects with for reciprocity and transitivity in 3 cycles and other networks. The exception being the out degree effect, but I think I can explain that by the fact that normatively, people in recovery houses are supposed to be friendly and help each other. There's a norm associated with that. And second, they're very small networks. So probably a threshold of friendships, like how many friendships is too much if you're, I don't know, let's say a middle school student, in a class of 200 kids. Well, it's well short of 200, that's for sure. It's probably well short of 100, which would be half the class, and probably more like 6 or 7, maybe, good friends. And after that, it's kind of hard to really think of other people as good friends. So it's a different situation when you're in a big network versus when you're in a small network. And so for all of those reasons, I find that positive parameter for out degree to be reasonable. Anyway, that's the way I would think about the results from this model. Provisionally, of course, because of the fact that the convergence was not great. But I'm going to go on here. I'm going to kind of build from here and see what happens. Make sense?
Yeah, John, and just want to mention that, again, for a class of 200, if I was a class, maybe 100 of them, I might say, well, they're friends, I know them, but maybe only 6 would be close friends.
Correct.
So there might be that distinction between friend and close friend.
Oh, absolutely. As a matter of fact, in one of my early studies of adolescence, we would have, we kind of stepped down the relationships in that way. We first asked the kids to, name all of their classmates that they spent free time with, outside of school. And quite typically they would name, 10 or 20 or sometimes as many as 25 or 30 friends or acquaintances, let's say, people that they had some contact with. But then we would ask them, out of this group, how many of them would you say are, what's the terminology we used? Who among this group are your best friends? Well, now you get down to 6 or 7, or less. It would be somewhere between 3 and 8 typically. So that exemplifies exactly how that works. Yeah. Yeah, no 2 ways about it.
Hey, John, it's a little mysterious why R-Siena decided to quit where it did, given that it's questioning its own convergence?
Well, you can set the convergence criteria, and basically what it will do is it will go, you think about it, it's an algorithm, okay? If it doesn't ever meet its convergence criteria, it might run forever. And you wouldn't know, right? Because how can it tell you? Instead of that, what happens is that after a while, and there's some things you can read up if you're interested as to what, how it decides what after a while means. If it runs and certain other criteria are met, but not your convergence criteria, it will just stop and it'll give you this message. So yes, it is a little mysterious, but it's not, you know, if you're really interested in exactly when it decides to stop under these conditions, you can find out.
Would you expect this would you expect this to get better if you reran it using these start values?
It very well might. In fact, I've done that a number of times, and quite often it does, yes. In this case, I think just because of the fact that I'm exploring, I'm going to add a few more variables to see if that makes things better. And simultaneously, remember, it's going to use those same start values anyway in the next model, right? So you can kind of kill two birds with one stone if another effect that you add isn't so colossally inappropriate, you know, either because it's irrelevant to the model, or you give it such a crappy start value that it's already lost in the wilderness, right? Having started off in a kind of a shaky place. But usually if you can get away with that, and you know, given the fact that, you know, sort of, well, time isn't money, but time is certainly science, and we can say that we'd like to be able to shortcut this process as much as we can, because it's already pretty laborious, you know, forward selection a couple of hours at a time for each model. I mean, geez, you know. So I found that often you can kind of cut corners a little bit and things work out okay, but not always. And sometimes you have to kind of go back to the drawing board. And it's not always clear what the problem is either. I mean, it could be anything from bad start values to you have no idea what you're trying to model and what the proper effects should be. And believe me, I've been in all of those places and everything in between. Okay. So, but good question. Definitely good question. All right. How are we doing on time? Oh, we're doing okay. Not bad. Let me see if there's one more model here I should, that one's not so good yet. That's really terrible. Finally, I have gotten a model where the convergence is good. Okay, you can see these values here are all pretty small. They're universally less than 0.10 in absolute value, and most of them are way below that. And your overall maximum convergence ratio is 0.14, where 0.20 is kind of the upper limit by convention. That's not hard and fast, it's just a rule of thumb. So let's see what this one had in it. Well, this one had in it the same out degree, reciprocity, transitive triplet, and 3-cycle values. And you can see that broadly speaking, those parameters are the same as they were before. I mean, they're a little different because, you know, from one iterative run to another, you never are going to get the same values out to X number of decimal points. In fact, the reciprocity effect looks even stronger here. Although I think the T ratio is better. It's around 3 now. Transitive triplets stronger, you know, with a T value of around 2.5. 3 cycles effect looks to be about the same. I think it was 0.38 before, and it's 0.39 here in absolute value. Now, in this case, we looked at the recovery factor. Excuse me, no, not the recovery factor. We looked at sex to see whether that made any difference. So in other words, are women, that we used to say people in women in female-only houses, more likely to have more friends than men? Well, if anything, the women are slightly less likely to nominate others as friends or good friends. But you can see that the standard deviation is bigger, standard error, I mean, is bigger than the parameter. So the t-value is less than 1, which is certainly not statistically significant. So I would conclude from that that there is no tendency, no systematic tendency for differential amounts of friendship choosing, just raw amounts of friendship choosing of males compared to females in this study. What about the attractiveness of individuals with a lot of time in residence as people you would choose as a friend? That's what the alter means. It means that it's a characteristic of the person that I am choosing that is making the effect here. And so basically a positive value here, which in fact we have, suggests that the more time in residence that that guy over there has, the more likely I am to choose him or her, as the case may be, as a friend. But you'll also notice that once again, the standard error is bigger than the parameter. T-value is less than 1, clearly not significant. So there is no systematic tendency in these data that makes people who have been in a house for a longer time a more attractive friendship partner than anyone else. Let that sink in. That's important. It's a negative finding, but it's important.
But John, the ego.
I'm just about to get to that.
Oh.
That one is statistically significant. This is interesting because it says that people who have been in a house for a long time are more likely to select others as friends than somebody who's been in the house for less time at their baseline interview. So what does that mean? Well, it means that indeed our question about whether people who have been in the house for a long time are more likely to are less likely to befriend newcomers and more likely, let's say, to create a little clique and then just stay within that clique. This would be evidence against that. It suggests that these people are expansive in their friendship networks, and that indeed the longer you've been in the house, the more friends or good friends you have. That could be simply a matter of how much time you've been there and how much time you've had to get to know people. Okay, but it might also be consistent with a norm of people who have been there for a while, helping out people who have not been there for such a long time. To figure out which of those was the case, of course, we would have to have a more complicated model. Let me see if I also ran something that had in-res similarity.
And is in-res, John, is that a fixed covariate? It
is, because that's the amount of time that you've been in residence at your baseline interview. So you only have one baseline interview. You only have, therefore, one in-res L value. Let's see, is this any different? Looks like the same model. I don't know why I ran that. Oh, I know, because I have some more okay, in this model compared to the other one, notice that in the behavior model here, I checked to see whether there was a effect of a person's sex on the tendency to for their recovery factor to go up or down. So this is a relative thing. Remember, 0 is male, 1 is female. It turns out that this negative effect indicates that males increase their recovery factor more so than females over the course of all of the periods, which is kind of interesting. Maybe they were worse off to begin with. We haven't tried to check for that, but that would be a possibility. I also wanted to see if there was a differential tendency for improvement based on how long you've been in the house at baseline. And surprisingly enough, there is not a statistically significant effect. You know, you can see this t-value here, 0.04 over 0.05 would be less than 1. It's not significant. That surprised me, and I'm a little concerned about that because our data seems to suggest that people who have been, you know, like Mike from your analyses, that most of the improvement in the recovery factor comes from individuals who have been not in residence for very long. So I would have expected this effect here to be negative, but it isn't. So I'm not sure what's going on with that. That's a bit of a mystery. But it's possible that that could be the case just based on other factors that I have not bothered to include.
So John, when do you decide which of the iterations you're going to go with? Because you've got, again, different results. When do you sort of say, okay, that's the one I'm going to sort of stick with?
There's no hard and fast answer to that, Lenny. I mean, you know, model building is as much art as science, to be honest with you. And by that, I mean that, you know, the considerations involved are theoretical, what you're actually seeing in the way of results, sometimes descriptive data or results from other analyses that we've done. For example, a lot of my thinking is informed by analyses done by Mike and others, indicating how things change and what their predictors tend to be. So I wish I could give you a nice formula for that, but I can't. I mean, it really just depends on your own experience, and it depends on what you think might be going on, ideas that you have about the factors that might affect tie formation or dissolution, or changes in the recovery factor, which are our two dependent variables. And learning how to think about that, you know, that's the same thing as learning how to think about any substantive area. There's no shortcut for that. You just have to know the literature, know your phenomena, I should say, that you're trying to model, and, you know, make your educated guesses accordingly. So we'll find out about stuff like that as we all chug forward, and we'll get to talk about the results and make decisions about where we go based upon where we are. And it's just, like I said, it's educated guesswork.
Hey, John, I had a question.
Of course.
So I ran the iterations, everything happened, it created in my global environment, that one, right? Mod 1.10.
Okay.
And I don't know what happened to what you're looking at. Where did it send this thing? Because I don't know.
Good question. It's going to get sent to whatever name you gave it when you did Siena model create. Siena model create is what determines that. So there will be something, like if I ran this model that used this object here as its algorithm, there would be an object called rfnetworkmodel.ad.txt over here in the files window. And that's what I would go look at.
Okay, that should be in my script, right? No one, your script, but.
Well, whatever. Okay, this is the model object or the algorithm object that was created, which has to be specified in the call to R-Siena 07, right?
Yeah.
So when R-Siena 07 does that estimation, it will put its results in a text file with this name as its primary name and .txt is the extension.
Mine's named RF models, and that's exactly where it is.
Fine.
Thanks.
Yeah. Yeah, a lot of navigational issues here, I understand. It gets to be second nature after a while, of course. Let me see if there's anything else interesting I can show you here.
And John, how would you interpret the effect size, like the sex effect on the recovery factor? Because didn't you have to convert that to ordinal?
Yes, I mean, basically what that means is, you know, this parameter here predicts well, remember, it's like an exponential model, right? So you know, exp of this is associated with a 1 unit change in the recovery factor. And in this case, we have a dichotomous variable, so this is a difference. The exponentiation of that is the difference in the change in the recovery factor as a function of the person's sex differentially. Okay, and effectively, what this does, what this is going to tell us here, is it can be translated into a probability of a person who is male versus a person who's female making a 1 unit change in their recovery factor as a function of their sex. Okay. The way this works requires a little discussion of the way the algorithm works, which you can read about, but I'll try to give you, it's probably better if you read about it. And for example, you could read about it in any number of places. But I think the Snyder's Van de Bunt and Steglich paper in social networks is perhaps the best place to start if you haven't read that. There is also, by the way, specific text within the Siena manual, which has improved greatly over the years, explaining how to interpret an effect. And let me see if I can point you to where that is. But basically the way it works is this. The algorithm is essentially a simulation of the set of stochastic differential equations given, or difference equations actually, because it's ordinal, given by the model specification. There's 2 dependent variables, the network and the recovery factor. They're interdependent potentially. Okay, I'm trying to find the. No, there's no. There we go.
Well, the reason I was asking is because
Yeah.
I see a significant sex effect on the recovery factor in growth models.
Yep. Good.
And I believe it's the same direction that you're getting.
Yeah, it is.
But
so that's a great indication of a great exemplification of how quite different models, like the growth models that you have and these models here, can produce quite congruent results when you're using similar predictors and similar dependent variables.
Yeah,
the difference is that I get to use affiliations that somebody has in the network as a predictor of their recovery factors, whereas you can't do that. Well, not directly anyway.
Yeah, that could be part of it, but also notice that your standard errors are a lot smaller than mine.
Fascinating.
And the gender is actually a house level variable because everybody within the house has the same gender.
Exactly.
So there could be some standard error underestimation in the R-Siena models if it doesn't know about the house, the nesting of subjects within houses.
Yep. Yeah, unfortunately, it doesn't. It's, in effect, an R-Siena model really doesn't have a way of directly talking about house level effects. The only way that you could do that would be to try to estimate an individual R-Siena model for each house and then basically meta-analyze them, which would, you know, now you're just doing a 2-level model, aren't you? You know, so your parameters are you take your parameters as being the things that you want to predict, and then you have a bunch of house level covariates, and you predict them in this population of 42. So it's like a non-simultaneous two-level model when you do it that way. And you could do the same thing with growth models, right? You could estimate individual slopes. I think that would be like two-stage least squares, actually, as opposed to a completely pooled like three-stage least squares model, where you basically do the whole thing all at once.
Yeah,
But
when I was on the web page at Oxford, I thought I saw something for the R-Siena test where they said they were experimenting with a multi-level option.
yeah, there is a multi-level option, but you can't still, there's no such thing as level 2 variables.
Oh, okay.
Okay, so it's multi-level in a kind of a way. Like you can see right here, there's something called multi-level network analysis, multi-group, meta-analysis. This meta-analysis is where you get to specify variables at the network level, which in our case would be at the house level. But the problem is that our networks are too small to get individual estimates, you know? So we're in that, if we had like networks of 50 each even, we'd have a fighting chance of specifying house level models, which we could then meta-analyze and everything would be lovely. But unfortunately, that doesn't work with networks of 5 to 10 for the most part. You'd drop out so many networks because you were getting non-convergence even on very simple models, that it's just kind of pointless. And so we're left with a situation where we have to do more pooling than we'd like to. And where we have to assume that
How about that Bayesian? It says Siena Bayes.
there is a Siena Bayes option, which I think works okay, but I've never really worked with it very much.
Because in your 11.3 there in your outline, talks
Yes.
about random coefficient models.
Right. The trouble with this is that basically the random coefficient model just is a situation where you allow your effects to have distributions.
Yeah.
Okay, so the results are distributional. But you still can't include house level predictors or network level predictors, even in Siena Bayes.
Okay.
So, but you can read about that. The one thing that you can do is, you could specify stronger priors. So you could constrain the model in the usual Bayesian ways, not using flat priors. And that might help you if you have a good reason to do that. But yeah, if you wanted to read that section on random coefficient, Siena Bayes models, Mike, and give me an opinion, I'd appreciate it, because you know more about Bayesian modeling than I do.
I'm looking at the little paragraph there where it says Siena Bayes is time consuming. So
yeah,
if
part of the problem is that it uses maximum likelihood, and maximum likelihood, I use a type of maximum likelihood anyway, right? Because we know that's kind of part of Bayesian modeling. And we also know that in R-Siena, using maximum likelihood means we only get to use one processor at once. So that whole, both phases 2 and phase 3 are just chugging away, you doing one simulation at a time. Yeah, that can take a while. I mean, even these models here using maximum likelihood would probably take, I don't know, 4 or 5 hours to run. But it could be worth it if the results are what we need.
John, could we, in the 42 houses, could we basically do a separate analysis for each of them, as you said before? Would that make sense to see if there's any variation in the 42 houses?
The problem is that with an N of 5 to 10, which is basically what we have in these houses, roughly, some are a little smaller, some are a little bigger, you're not going to get good results for that. There's just not enough data there to estimate any kind of model that has any kind of complexity. Instead of that, what we basically do is we pool the effects across houses, and that gives us a fighting chance of getting what amount to average parameters that are true across the houses. That makes sense. At the present time, there's not really a great way to solve that problem when your individual networks are this small. You might remember that that I wrote we wrote a paper a year or so ago about a sort of an intermediate way to do that, where you could kind of empirically group together the houses and basically pool the estimates within those groups. And you would do so on the basis of some kind of a priori similarity of the houses. It could be region, it could be size, it could be, well, size wouldn't be great, because the problem with that is that with your smaller houses, you would have, you could have a lot of instability that you introduce as a result, but it's possible, you know, you might do that. Certainly gender of the house could be an obvious way to decide to pool your results. And then you could combine those in a meta-analysis. You probably wouldn't be able to have house level predictors if you only had 3 or 4 subsets that you were combining, but at least that would allow you to free the individual parameters that you were estimating. And the presumption would be that you would get a better overall sense of what was going on as a result of that that specification. But it's
John,
a kind of a kludge. Anyway, the answer to your question, Lenny, is probably no.
So John, in our first paper we published in Journal of Community Psych, we actually divided the houses into 3 groups.
Yep.
And those 3
Where we got the idea.
Could something like that be done?
Right, that's what I was just talking about. That's following the sort of a priori clustering or a priori pooling procedure. So yeah, we could do that. We haven't gotten to the point of needing to do that yet, but if we hit the wall on modeling by assuming complete pooling, which is kind of what we're doing right now, then you know, basically what we do is we assume that any relationship in any house is the same as any other. And undoubtedly that's much too strong an assumption, but you have to start somewhere. But if we start to run out of gas with that approach, then what you were just suggesting and what we proposed in that group dynamics paper would be a good next step. Okay, I got a little off topic there. I'm just trying to find, here we go. Chapter 13, parameter interpretation. I strongly recommend that you all read that chapter in the R-Siena manual. And it will tell you, it will go into some detail in ways that I could do, but it would take a whole separate talk to do that. That might be a good topic for next Friday. Speaking of which, well, we still have a little time left. What would you guys like to see in the 15 minutes we have left?
John,
ahead,
just one idea is that maybe we can spend the rest of the time, you know, or between now and Tuesday when we'll come together again, just getting a chance to do the things that you've suggested, which is play with the data, and then we'll have questions that we can bring to you on Tuesday. How does that sound?
That sounds terrific. One thing that I could do before I go is I can actually start a model running. I'm not going to. Don't say. So I can start this model running here and kind of show you what you're seeing, which can be a little bit helpful. How do I do that? I'm not going to send myself this email. quickly, I just want to remind you that you can use the setup email function once I push it up to, well, if you have access to RH Tools, or excuse me, to JML Utils directly, you can just pull it and rebuild it. If not, I will arrange to post a binary of it, and also a source which you can build if you like are running on a Mac or something, because you can't use a binary that I created on a Windows machine, of course. But I will arrange to give you guys access to these functions. They've changed now so that they have parameters, and you can give it a Gmail account of your own, and you can also give it a, you can now tell it where you want the email sent. So if you want to have it sent to your DePaul account or something like that after the run finishes, you can do that.
John,
And
on Tuesday, I was just kind of wondering, maybe we could look at some of the results across the three relationships of.
I think that'd be great. And I now have results across all three,
Yeah.
and you guys probably do too. And we can maybe start to compare some
Yeah.
actual substantive results.
And the other thing that would be kind of fun is if we could run a model that basically looked at close friendship versus just because you already have one with friendship and close friendship. Does
Yeah.
it make a difference in terms of the results? That would be kind of cool to see.
Why don't I go ahead and, yeah, I've been inspecting the advice network a little bit and finding out some interesting things, but more questions than answers there. What I can do is I can make sure that I've run at least a couple using a definition of friendship that's more restrictive. So only the close friend is considered to be a friend. And maybe I can also try one where I've got the stepped friendship networks, right? The close friend within friend specification. And I can see whether that gives us anything interesting too. And it might be a good basis for going forward with future analyses of friendship. How's that?
Yeah, it sounds great.
Yeah. This is all, by the way, I mean, I'm just dashing these things off, but even thinking about these models, running them and figuring out how to specify them and interpret them is a lot of work. And it's going to take more than the hour that we have next Tuesday, I think, to go through all of that. But we can make a start. And so this is all to the good. Let me just see one thing. If I want to see if there's anything in the R-Siena manual on nested networks. No. All right. Since you had mentioned it, Lenny, there's a place where you can talk about how, where you can specify networks as transitioning into each other on the basis of their value. And I'll see if I can find that reference and make it available to everybody so that you can read about how that works. It's a little kludgy, not quite what you'd want, but it actually gets the job done, nevertheless. Okay, so much for that. And so much for that. Great. So if you want to hang around for another 5 minutes here, I'll start this model and I'll see what, let's see what we get. Okay, so I'm just rerunning the last advice network model that I specified. The spec is given here. What I'm doing is I'm not doing anything at all to predict the recovery factor, but I'm looking at whether similarity by age might have an effect in addition to these effects associated with reciprocity, transitivity, and 3 cycles. The results that I had previously for this were given here. Okay. I'm already writing into that, so I can't look at it. but I can see what the what's going on here. Whenever you start out this start up the model, you'll get this little feather icon down here. If you click on that, you'll see an X window that opens up, and this basically this window gives you, if you know what to look for, something about here. There we go. Gives you something about what the program is doing. Right now, it's doing some preliminary stuff prior to actually starting its estimation. So it's basically doing initialization. It's figuring out, okay, you know, what should the start values be? You know, I've got to set up my different estimation objects that I'm going to use for the process. A lot of under the cover stuff that's going on here. Mysterious C++ code is running. By the way, I've been down in the bowels of that C++ code, and it's broadly understandable, but not very well documented, I'm sorry to say. But in principle, if you really want to, and you're a good C++ programmer, you could go down in there and you could figure out what it was doing. What it's going to do next is it's going to start phase 1. And what it's doing during phase 1 is it runs a bunch of simulations to figure out how its start values compare to the data in terms of what the matrix of partial derivatives should be for how to change the parameter values once it starts making estimations. So it's a typical hill climbing algorithm, but for that, it needs to know what the partial derivatives should be in terms of figuring out what the direction of most improvement is in the parameter space. And this will mean nothing to you if you don't know anything about these algorithms, but it might mean something to you if you do. Okay, very soon it will probably start doing phase 1.
When you do that, John, does that tie up your RStudio session?
Did it tie it up? Yeah, it can't. I'm not going to be able to do anything else in RStudio. I mean, I can look at stuff, but if I try to execute stuff, it won't execute until after the R-Siena finishes.
Okay.
So yeah, I mean, that's a good thing to know about. Whatever computer is running this thing, you can do other things with it if you saved a few nodes. And by the way, you have what, like a 32 node server?
36.
36, yeah. There's no point in using more than 10 or 12 of those nodes. It won't really improve the speed of the algorithm because the way the algorithm scales, it's already doing about the best it can after you've used that number of nodes, unfortunately. I wish the improvement scales linearly, but no such luck. So that would certainly enable you to use that computer for other stuff. You just couldn't do other stuff in that particular R-Siena session because it would be busy doing this. Make sense? Okay.
Yeah.
All right, we'll see whether, I keep saying any minute now, this thing will start running phase 1, but it's still doing preliminaries. By the way, this picture here, that's the central square in Siena, Italy, which is where Tom gave the first public talk on Siena, which subsequently became R-Siena after we reprogrammed it from Turbo Pascal to R.
But I think
nice?
I've got an idea that will be similar to the violence exposure.
I'm sorry, somebody was saying something, I didn't hear him.
So no, John, this was, I just put myself off mute. Why don't we kind of end things?
Here we go.
Oh, okay.
It finished running phase 1 and now it's already, and apparently that was really quick in phase 1. Now it's actually estimating the parameters. And here you see, notice there's 19 parameters over here in my spec. And here's your 19 parameters. And these are the current values that it's using for the simulation run that it's working on. And you can see they're already quite different than whatever these initial value parameters were here. By the way, the initial value parameters are not whatever was in remember I gave it a prevance value here. What you see here isn't the values that the previous run included. That's in a different place, unfortunately. I wish that wasn't true, but in any case, these are the values that it's working with right now. Now, what can you tell by all of this? You can tell over here how different the predicted versus actual values are for this particular parameter. And what you should see as these iterations go forward is that these deviation values get more or less generally smaller. It's not monotonic in terms of that happening, but as a rule, they should be approaching absolute value of zero in absolute value. If they're getting bigger in absolute value, then your algorithm is lost in the wilderness. And if they really start getting big, like they start getting up into the thousands and stuff like that on a regular basis here, you might as well just interrupt. Or another thing you could try would be to restart, which basically means it's going to take the value that it's got right now and it's going to restart the iteration algorithm using these current values. So those are both alternatives. Generally speaking, if you're smart about specifying the model, that shouldn't be too big of a problem. And this looks fine. And this all looks just great. It's still kind of wonking around in 19 dimensions, which is the size of your state space, trying to figure out what the best parameter values are to make the best predictions that it can. That is to say, with the smallest deviation values here. Okay. These quasi-autocorrelations are basically autocorrelations of successive values of the parameter vector. And they should be approaching zero or ideally be negative in order to give an indication that the parameter vector is getting into a place in the parameter space that's somewhat close to a good solution. Because what that means is if they're negative, it means they're bouncing back and forth between positive and negative values. In effect, they're sneaking up on the correct point by overshooting it and then undershooting it and overshooting it and undershooting it and hopefully each time getting closer, all right? When it's, if they're just negative or if they're just positive, then it means that you're moving in a monotonic direction of the parameter getting bigger or smaller. When they become negative, now it's iterating around a point, which means it's close. And you can see, if you've been watching here, that in general, these quasi-autocorrelations, more and more of them are becoming either negative or at least approaching zero, right? So considering that and considering the fact that the deviation values are quite small and getting smaller on the whole, we can say that the parameter, that the estimation process is going ahead pretty well. That's what you can infer from this. And in fact, we're almost to the point where all of these values are negative. And when they're negative and small enough in absolute value, the algorithm will jump into subphase 2, where the iterations on the parameter values are even smaller. So in effect, phase 1 gets you kind of into the ballpark. Phase 2 makes smaller changes. Phase 3 makes even smaller changes, and phase 4 makes smaller changes yet. You can set the number of subphases, by the way, to be any number you want, but the defaults are generally okay.
John, on that note, we've been going for about 2 hours.
Yep.
Maybe we can wrap things up. And
Let's do that.
And all I can say is this has been great, and we will continue on Tuesday.
Sounds great, folks. Thank you for your attention. A bunch of great questions. Just feel free to ask me questions as we move forward here. You know my email. Get a hold of me, and I'll get back to you as quick as I can with help.
Thank you very much, John. Very helpful.
All right. You're welcome. Okay. Good to see everybody.
Thanks, John.
Take care. We'll see you next Tuesday.
Okay.
Thank you.
Okay. Bye-bye.